So we've done the boring alkanes. Now we're going to move, staying within hydrocarbons, to molecules with functional groups, the fun bits, starting off with alkenes that of course contain a carbon-carbon double bond. So if we just look at this again, you've got the organic counting. The infix part now is going to be ene because we're dealing with alkenes. There's no one carbon alkene because of course you can't have a carbon bonding to itself. So the simplest one is ethene. There it is, drawing it prettily like that. Now if we note again the homologous series for the formula of that is C2H4. Now we'll move to the 3 carbon propene. There's two ways to draw it, C3H6. Butene, C4H8, pentene, C5H10, hexene, heptene, octene, nonene, and decene. Now I hope what you notice here is that the homologous series formula for this is CnH2n. Where have those extra 2 hydrogens gone compared to the alkane, compared to the CnH2n plus 2? Well, again, what we've seen here is, as we did when we made the cyclohexanes, we got one more carbon-carbon bond, so 2 less hydrogens. Every extra carbon-carbon bond, whether it's in a multiple bond, whether it's making a ring, reduces the number of hydrogens in the homologous series by 2. Now, depending upon which A-level board you did, you might or might not have encountered alkynes with a carbon-carbon triple bond. Very much the same idea though. Right, again, the infix changes because now we've got a triple bond, so it would be YN instead of EN for the double bond, or AN for no extra bonds at all. No one carbon alkyne, ethyne, formula C2H2, propyne C3H4, butyne C4H6. You can continue yourselves. What is the formula for the homologous series? Well, we again have made an extra carbon-carbon bond, so we've lost 2 hydrogens. So you can see if you calculated, it's CnH2n minus 2 there. Now at this stage, I'm going to introduce, and we'll come back to this towards the end of the video, a very important concept called the double bond equivalent, or DBE. And this is related to the maximum number of hydrogens a given number of carbons can support. Okay, double bond is 1 double bond equivalent, triple bond is 2 double bond equivalents because we made 2 extra carbon-carbon bonds, and of course a ring is 1 double bond equivalent. Now there's a couple of little formulae here that we're going to use, but I also want you to think through it. Okay, the double bond equivalent can be determined by taking the expected number of hydrogens minus the actual number of hydrogens. So that's the difference in the number of hydrogens divided by 2, because of course each double bond equivalent gets rid of 2 hydrogens. So another way to put this is we expect hydrogens, 2 carbons plus 2. Take away the actual hydrogens over 2. So for example, imagine this, a fun little molecule here, cyclopentadiene. Okay, its formula, if you count it up, is C5H6. Well, let's figure out how many double bond equivalents there would be here. We would expect there to be 2 times 5 plus 2, which is of course 12 for 5 carbons. We've got 6. 12 minus 6 over 2 is 3. The organic chemists can do maths, can't they? Where do those double bond equivalents come from? Well, we got 1 ring and we got 2 double bonds. Okay, so we'll practice this a little bit in class. It's not a hard concept, and it can be extremely helpful in giving you a start when you know the formula of a molecule and trying to figure out what its actual structure is. Now this is, I've titled this, continue the title, the fun bit. It's actually not that fun, but what I'm doing here is I'm listing out the different types of functional groups that you might encounter over the next couple of years in the order of their priority. Now you might remember when I talked right at the start of the first naming group that the suffix is determined by the dominant, the highest priority group in the molecule. And so here we have different types of functional groups arranged by their priority. So if you have a carboxylic acid in the molecule, that's what's going to be determining the suffix. Okay, so anyway, this I would suggest you print out these tables on these next few pages and just have them as reference. Okay, carboxylic acid, you should be able to recognize that. That is the group there, carbon double bond O, then OH. And the examples I've got ethanoic acid, because that is the usual suffix, 2 carbons, 1, 2, enoic acid, the an of course being the infix, and then the oic acid tells you about the acid group there. Sometimes you'll see, as you might have seen from your A levels, what I would call benzoic acid is benzene, carboxylic acid. Again, that carboxylic acid is the whole suffix, which is kind of funky, but that's how you name it in some cases. Now, you should have seen carboxylic acids before. You probably haven't seen a sulfonic acid before. These come up occasionally when you're talking about synthetic processes as protecting groups and reactive groups and so on. So you can see what it is here. It's a S double bond O, OH. By the way, if you think back to how I draw Lewis structures, if I'd been drawing this Lewis structure using the method, I would have had single bonds here. No biggie either which way you do it, but organic chemists like to put the double bonds in because organic chemists prefer formal charge over the octetral, probably because most of them can't count as high as 8, so they don't worry about such numbers. But anyway, that was an aside. Here's the sulfonic acid group here. So this is benzene, sulfonic acid. You got sulfonic acid in the molecule, you don't have the carboxylic acid in the molecule. That will determine the name by determining the suffix. Next one, ester. You have encountered these before. Esters come, if you remember, from alcohols and carboxylic acids. The name is essentially propyl, which in this case comes from the alcohol, and then the ethanoate. The OAte part comes from the acid, so here you can see it's some ethanoic acid. So this is propyl ethanoate. There are, should you have the weirdest molecule in the world in which you've got an ester group in one bit and then a carboxylic acid up the other end, so the carboxylic acid or a sulfonic acid would take priority, then you have to describe the ester as an alkoxy carbonyl, but I've never seen that used in a name, so I'm not going to mess around giving you the example of it. Same idea if you've got an acid halide. Again, these, remember, are derivatives of the acid group, so even derivatives of the acid groups have got nice high priorities. So ethanyl chloride here, it's the ioyl chloride that is the important suffix there, and of course ethane, the 2 carbons, and again we don't have a carbon-carbon double bond, so the infix is an. Continuing on, that's another acid derivative, the amide. Here is prop, so 3 carbons, and because there's no carbon-carbon double bonds or triple bonds in there, and then the amide group, C double bond O, NH2, again should be familiar to you from A level, something that you'll probably never again see in your life. Carbamyl or amino carbonyl would be the prefix that you use if one of the top 4 priority groups are also in the molecule. Again, highly unlikely you'll see that. One that you've seen but probably not studied in any great detail, even though it's a really cool group, what I would call a cyanide group. It's actually a nitrile group. So here again you can see ethanol nitrile there, 2 carbons, and the group is a nitrile group. Aldehyde you're familiar with, because an aldehyde has to come at the end of a molecule. It's got a pretty high priority, higher priority than its friend the ketone. So propanal. If you do have an aldehyde there as an extra sort of stuck-on group, or the aldehyde group, its abbreviation actually goes back to the old-fashioned way of doing things, 4-mile, which is the old name for 1 carbon. So 1 carbon with a C double bond O stuck on that. Should you have a molecule in which the aldehyde is accompanied by a higher priority group. Ketones, of course, you've studied at great length. The C double bond O is not on the 1 position because that would make it an aldehyde. So we've got one where it's on the 2 position. Again, wouldn't actually need to put that 2 because you can only have 2 butanone. There's only 1 ketone from a butane chain. But anyway, and should again you have a higher priority group in there, which actually I have started to see these ones, really never seen most of these other ones. But at least, you know, in a lower priority setting, I have seen a couple of molecules where the ketone is not the top priority. So oxo, nice easy one to remember, is the prefix that you use for that. Alcohols, of course, you're very familiar with. Again, likely that you're going to see ones in which the alcohol is not the dominant group, so hydroxy being used, but ol is the suffix for an alcohol that of course you are familiar with, so that's ethanol. You might not be as familiar with a sulfur alcohol, a thiol. Prefix is mercapto. Anytime you see mercap or thio, it kind of should give you a clue that there is an sulfur around, so ethane thiol would be the sulfur equivalent of ethanol. Amine, the last real priority, and then of course we talked about alkynes and alkenes, where we have discussed those previously. There are functional groups which will never ever ever lead to a suffix, so you can see if you've got a halogen in there, as you might be familiar with, fluorochlorobromo iodo, and then ethers and azides and nitros. Give you a few examples of some of these. There's your ether. Okay, alkoxy is the ether group stuck onto an ethane. This is of course what you would have called in the old days diethyl ether, or just the ether that knocks you out. Azide is N3 and nitro is NO2. So these are the functional groups that you will encounter. Like I say, keep this charts so that you can refer back to them, particularly in terms of the priority as you need. Highly unlikely you'll see some of them, very, very likely you'll see others. Some of them very intuitive, like the halogens, other ones not quite as intuitive. Now, before we leave this naming / functional groups little part of the thing, let's go back to the double bond equivalent, okay, because we can actually think a little bit more about that, because now we're moving into where you've got other atoms other than just carbon and hydrogen atoms. Now, every halogen that you have in a molecule is essentially just a pseudo hydrogen. So if you've got one halogen, we're going to use the abbreviation HAL in our formula for that. Well, then that's an extra hydrogen that you can think of in the formula. Oxygens and other chalcogens don't have any effect at all upon the double bond equivalent. So for example, if you think of ethanol, C2H5OH, C2H6O, 2 carbons, you would expect to have 6 hydrogens, therefore having the oxygen in there has not affected the number of hydrogens. Every nitrogen or other pnictogen adds 1 to the expected number. So therefore here's the formula, which we will play with. Probably on a Kahoot. I know that makes you joyful when we're actually in class. Double bond equivalent is, well, how many hydrogens do we expect? Twice the number of carbons plus 2, plus the number of nitrogens, because each of that adds to the expected number. Subtract the number of actual hydrogens, and then also subtract any halogens you have in there, because those count as hydrogens, and then divide that by 2. So a very fast 25 minutes combined over some naming. We'll practice naming as we go through in our different types of molecules and when we get into different types of reactions where you will be taught by a real organic chemist other than me, the fake one. See you in class.